a big application of implicit differentiation is to multivariable calculus. Briefly introduced multivariable calculus last time. Let me briefly introduce it again, reintroduce it with another more complicated example. Look at this multivariable function. F of xy equals 3x squared times y plus y cubed minus x cubed minus 3x squared minus 3y squared. Yikes. That seems like a complicated multivariable function, and I would say it is. If I was going to write it by hand, I'd write z equals f of xy equals 3x squared y plus y cubed minus x cubed minus 3x squared minus 3y squared. We're going to consider this example today, and we'll consider it in future days as we talk about the Calc 1 content in addition to the multivariable calculus content. Why are we doing multivariable calculus? Because I do think it's a good idea to introduce it at this level, as you might say, an application of what we're doing in the actual book, including right now implicit differentiation. Most mere mortals, including myself, cannot graph this thing very easily without technology. I include myself in that. If I were told to graph this without technology, I'd be like, oh, I don't know if I can do it. I think I probably could eventually, but it would take a while. But the technology is nice. We can certainly make a graph of this with technology fairly quickly. Plot 3D in Mathematica will make a plot. Let's let x go from -3 to 3 and y go from -3 to 3. This will make a basic plot right there. It's a surface in three-dimensional space. There's a picture of it. Not too exciting. Maybe we want to go in closer to the origin. I think that's where all the interesting stuff is happening. Just doesn't look too much different. We do see, though, that it is, you might say, if you're imagining this as being like a field you're walking over, you might say it's slightly hilly, right? There's like a slight hilltop right here, maybe a slight valley back here. See where the cursor is there? Calculus ultimately is all about finding, in derivatives at least, it's all about finding extreme values of functions. Where is the function highest? Where is it lowest? In Calculus 1, that's one of the main applications we talk about. And you can talk about this with multivariable calculus functions as well. Maybe if I restrict the plot range in the vertical direction, we might see it better. Plot range, let's go say -10 to 10. Let's see if that looks a little bit more pronounced. Yeah, a little bit. Let's even go -5 to 5. Yeah, now we're seeing the hills and valleys a little bit more pronounced there. That's a surface plot, a two-dimensional surface in three-dimensional space, right? As x and y vary over the plane that's horizontal, the z-coordinate, the third coordinate, varies. And if you plot all the resulting points, you get a surface like this. It's easier to draw by hand a contour plot of it. These things, which I need more of, not that many, are called level curves. It's like looking at a map of a mountainous region. What you're seeing here are curves of different elevations, different heights in the z direction for the three-dimensional plot. And it's never done this before, but Mathematica here today and last time seems to, wherever the cursor is, you can't see the numbers so well. And I know it's small for people in the back. Anyway, that number there says -2.2. Along that curve that the cursor is by, the height of the function is -2.2, meaning the output, z, is -2.2 along this. Along this one, it's -1.65. It's hard to see in back, I know. This one says -1.1. This one says -0.55. Are there any positive values? Yeah, over here, 6.6 is what that one says. 4.95. You can think of these as elevations. You'd have to go to the upper left to go up a mountain. You'd have to go down to the lower right to go down a valley. Actually, darker corresponds to lower values and lighter corresponds to higher values. It's kind of like heaven and hell, I guess. Okay, light and dark. How is this relevant for implicit differentiation? Implicit differentiation can help us analyze these curves. For example, slopes of their tangent lines. How so? Let's see. Well, I'd have to have an exact point on one of these, which I didn't think about ahead of time. Okay, let's just do an implicit differentiation here for one of these curves. I'm not going to specify, well, I should probably specify which one. Let's say we're thinking about this curve where the output of the function looks to be negative 1.1. I wonder, let's just pretend the output's negative 1. I could actually plot that particular curve by itself if I want to as well, by modifying the code a little bit. I can put an extra equals negative 1 in here, and that'll draw the 1 curve where the output is negative 1. I might wonder, along this curve, what are the various slopes at various points? Okay. What you need to do is you need to set the function equal to the output that I said, negative 1. 3x squared y plus y cubed minus x cubed minus 3x squared minus 3y squared, set it equal to negative 1. That equation involving x and y defines a curve. It was the curve we were just looking at a minute ago. How do you find slopes along the curve? How do you find derivatives of y with respect to x? It's not so easy to solve for y as a function of x, is it? It's a cubic. Is there a cubic formula? Actually, there is, but it's super complicated. So what do you do instead? Do we have to use that super complicated formula? No, we don't. We do something better. We use implicit differentiation. What is that? We make a big assumption. We assume, and this is a big assumption, though it does turn out to be valid for many of the points on the curve, that y is a function of x. Y is a function of x. Now, technically speaking, that assumption is wrong for the entire curve. It's invalid because that curve that you see right there fails the vertical line test. It's not the graph of a function. There are vertical lines that go through it more than once. However, it will be past the vertical line test if we focus in near certain points and ignore and only look at little pieces of the curve and ignore the rest of the curve. That's called local. Locally speaking, near points that have tangent lines that are not vertical, it will pass the horizontal line test if you just focus on a little piece of the curve. And that's what our assumption is really doing. Near some point. I'm not specifying what the point is because I don't know what the point is. I don't know what the points are on the curve exactly. We want to find dy dx. Goal. Find dy dx, the derivative of y with respect to x, by differentiating both sides with respect to x, keeping in mind that y depends on x because of my assumption. This is the hardest part. I'm thinking of y as a function of x. So listen very, very carefully. When I look at 3x squared y, I say to myself, y is a function of x. I need the product rule there. My left function is 3x squared. My right function is y, which is a function of x. I need the product rule. Left d right. What's the derivative of the right? What's the derivative of y with respect to x? It's not 0. It's not 1 either. It's dy dx. That's what it is. Y is a function of x, but I don't know what function of x it is. That's okay. Its derivative can still be represented symbolically as dy dx. This is weird, but this is what's done. That's left d right plus right d left. The derivative of the left, 3x squared, is 6x. And the right is just y. Y is a function of x. I mean, you could write f of x in place of y if you wanted to, but you don't know what f of x is. I just used the product rule there to differentiate that, assuming y is a function of x. This is not easy for people. It takes work and thinking exactly about the words that I'm saying, the exact words I'm saying. Now differentiate y cubed with respect to x. The answer is not 0. The answer is not 3y squared. Although it's almost 3y squared. It's 3y squared dy dx. What did I use there? I used the chain rule. The outside function is the cubing function, whose derivative is 3 times the variable squared. The inside function is y, which is a function of x, and whose derivative can only be written as dy dx, or y prime if you prefer, to simplify the notation, but I'm trying to use the dy dx notation. Y is a function of x. It all goes back to this assumption. Subtract the derivative of x cubed, that's just subtracting 3x squared. Do I need to multiply by dx dx? I guess you could, but dx dx is 1. So you don't need to write it down. The derivative of x with respect to itself is 1. The derivative of minus 3x squared is minus 6x. And the derivative of minus 3y squared is minus 6y times dy dx. The chain rule again is used. Anytime you see a y when you're doing implicit differentiation, that's what this is called, implicit differentiation, because I'm assuming this equation defines y, we say implicitly as a function of x as opposed to explicitly. We don't know what f of x is. We don't have an explicit formula. But I'm assuming implicitly, you might say, without an explicit formula, that it's true that y is some unknown function of x. Actually, Mathematica can find the function. I'll show you real quick. In Mathematica, we can take this equation, f of x, y equals -1, and solve for y. Do we really want to do that? Yeah, okay, that's why we don't want to do it by hand. You want to do it by hand? That's the answer. There's 3 answers here, but this is the real one. The other 2 are complex answers. That's the answer for the unknown function of x. That's why we don't want to solve for that by hand. Instead, we want to use implicit differentiation. Okay? We're not done. We need to differentiate the right side too. The right side is a true constant, -1. Its derivative is 0. By the way, if I had picked a different constant there, like -2 or +5, I'd still get a derivative of 0 there, and I'd still get the same expression for dy dx, but it would be a different curve with different points that have different slopes ultimately. Because whether a point satisfies this equation depends on what the right-hand side number is. So what do you want to do now? We want to find dy dx. We need to solve this equation for dy dx. It doesn't look so easy. Well, it's easier than it looks. It is a linear equation in dy dx. There are 3 terms that involve dy dx. This one, and this one. Factor out the dy dx out of those terms. What's left inside the parentheses is 3x squared plus 3y squared minus 6y. With the terms that do not involve dy dx, put them on the other side of the equation. 6xy gets subtracted from both sides to give you a minus 6xy on the right side. -3x squared, you have to add 3x squared to both sides to cancel on the left to give you a plus 3x squared on the right. Same kind of thing with the minus 6x, add 6x to both sides. Now divide both sides by this expression right there. dy dx is negative 6xy plus 3x squared plus 6x, all divided by 3x squared plus 3y squared minus 6y. That is the general form of the derivative. Now we're almost out of time. All I have left to do here are just make some comments, but you got to listen carefully to these comments. Okay. We are used to writing derivatives, dy dx, to be functions of x with no y's in them. Hey, there's a bunch of y's in there. Can that be right? It is right. Realize y is a function of x. So if we use the formula in Mathematica, we could replace all those y's with what's highlighted here, and we would get a function of x, a very, very complicated function of x. So we're not going to do it. Second thing to realize is that this will give you the slope of the curve at any point on the curve. But you've got to know the coordinates of the point before you can plug it in. Unfortunately, I didn't think carefully enough about this example to find specific points on this curve. I suppose I could use this formula here to find a specific point. Like I could do this, I could take that and I could plug in x equals 1 into that, for example. It looks like the point whose coordinates 1, 1 plus the cube root of 2 is a point on the curve. What's 1 plus the cube root of 2? It's about 2.26. The point whose coordinates are 1, 2.26 is a point on the curve. Where is that point? It's actually way up here. It's off the graph. It's part of the curve up here. Up here somewhere. The slope there looks like it's negative. If I plug that point into this formula, x is 1, y is about 2 point whatever I said, 2.56 or something. I think we'll probably get a negative slope. Theoretically, you could also use this equation to figure out where the slope is 0. A fraction is going to be 0 where the numerator is 0. You'd have to set that thing equal to 0 and solve for y as a function of x. Well, that gets tricky. You also want this equation to be true. It would be pretty complicated. This is a pretty complicated problem if I'm going to do those kinds of things. The examples in the book are easier. Theoretically, you could also figure out where the slope is infinite, where the tangent line is vertical, by setting the bottom equal to 0. And also wanting that equation to be true. Again, it would be complicated. These comments are important conceptually. Okay, so you are going to have an assignment from the section. There are examples in the book. There are more examples in the extra video I made. Calculus has got a lot of content to it. We really don't have time for all the content in class if we're also going to go over quizzes, for example, like we did today. So, yeah, there's the extra video, problem-solving video where I go through more examples. You got a week. See you next Wednesday.